All right, today's video, the next lesson is integration by parts. And this would be something that we would use kind of like when you see a product in an integral and none of the other resources. It doesn't work with U sub, and there's no simpler techniques that we previously learned that would work. We couldn't multiply it out or do anything different with it. So this is a product rule for integration, and it's called integration by parts. So it's basically like we're going to work with an f function and a g function, and usually these two are not related. So like if it was a polynomial and it was something times something else, we could multiply a polynomial by a polynomial and get a new polynomial that we could probably integrate. But this is a lot of times it's going to be something that's not related, and other methods don't work. Okay, I found a resource that actually someone had went to the trouble of making a PowerPoint slide presentation where they were trying to show their students the geometric interpretation of what you're actually doing, or how integration by parts actually came up. What you need to be able to memorize, and what we're going to be using continually in this lesson, is this right here. This is the integral of two things that are related. I have u and I have dv, and that's going to equal the product of u times v minus the integral of v du. Now that kind of probably sounds like Greek. You're just a bunch of letters and numbers right now. But let's take a look at how this plays out. This is set up, instead of having the x-axis and the y-axis, we're actually doing this with respect to v's and u's. I'm sure it's probably because x's and y's are used quite a bit, and so they don't want it to be confused with other things that you've done previously. So imagine some curve, and this would kind of be like where you might say, you know, y is equal to f of x. Okay, only we're using u's and f of v. Okay, so same thing, we have a curve. All right, now what we're going to do is we're going to define from v1 to v2, kind of like x1, x2, some area under the curve, which we've done before. So the integral from v1 to v2 of the integral of u, because u is that function line, dv with respect to v, because v is the x. It's kind of like your x variable, so we usually do it with what? dx. We would be similar to us doing something from a to b of, let's say, function y with respect to x, or you usually see it like f of x dx. All right, so it's just, don't be confused by the notation. Just understand that they're transitioning and using u's and v's. So we're looking at the same area that we've worked with before. Now we're going to represent kind of like the opposite side of the coin. We're going to look at the sideways. This is with respect to the vertical axis. Usually we have always worked with respect to, you know, the x-axis. Being the case, we're always finding that vertical. That seems to be what comes to mind because we always say area under a curve. Now what we're going to do is we're going to actually start talking about area under a curve, but with respect backwards horizontally, which would be back toward the y-axis. We have briefly looked at some integrals with respect to y, but we don't do it all that often. Okay, so again, you can pause the video, take some time, kind of let this soak in if you want to. This is not going to help us solve the problems that we're getting ready to do. This is just trying to let you see and understand that we didn't just all of a sudden do some mumbo jumbo and boom, here's something you have to memorize. There is a rhyme to a reason. The integral is equal to u times v, because if you differentiate, you would have to do it from some number to some number minus what we've done to the side. So I've tried to kind of draw that out. All right. This represents in another way what it would look like if you had broken it off into squares. Okay. Again, trying to talk about areas. Notice the notation looks similar. Pause the video if you want. Let this soak in. I'm not going to take time to break this down. I want to go ahead and get to the problems. But I just want you to see there are resources out there where you can look and find where did this integration by parts formula come from. All right, here's the formula. This says if we're going to take the derivative of u times v. Remember I said this was like the product rule. So if we take the derivative of u times v, you would take the derivative of the, or keep the first the same, times the derivative of the second, okay, plus keep the second one the same and the derivative of the first. So that's just our product rule from derivatives. But then what we're going to do is we're going to end up integrating this, okay. So I'm going to slide down. You can pause the video anytime you need to. And I've tried to make notes to actually say when you take the derivative or an integral of a derivative, you basically undo what you did before. These two kind of sort of cancel each other, and I end up with just what I started with. That's the second fundamental theorem of calculus. Then we're going to approach this as though it was an equation. We're going to subtract the integral v du from both sides. And that's what ends up, when we solve for u dv, that's what we end up with our integral. Okay, so it's almost like we're taking the integral of u dv, and we're going to end up with this right here. That is the integration by parts formula. All right, so here's where your notes start. You do not have a copy of the previous ones. Like I said, I was trying to come up with a way to show you how it came about. But now I'm interested in letting you know how do we actually apply this new technique. All right, so the integral of some u dv is going to be the product of u times v, and I'm going to take the integral of another part. So I'm actually going to have to do a lot of different things. This does take some practice. I wish we had actually had time to do it earlier. It was probably my bad. I probably should have done this right before spring break, before we actually jumped into volume. And we'll probably move that to that section. All right, here we go. It's also known as the product rule for integration. This strategy seems to work for things that are unrelated. They seem unrelated. So you don't have a polynomial in something. You maybe have a polynomial in an e. Or maybe you have a trig function and a polynomial. Or two things that don't seem to work. And you've tried u sub and you just don't have the things you need to do u sub. All right. This is something that you won't need immediately, but as you start working some of the later problems, a lot of times students have shortened this to lipit. This is the order of selecting your u. How do you know what part to be the u, and how do you know what part to be the dv? So I'm going to do logs and natural logs first. Inverse trig functions, we don't see those too often, but they do show up sometimes. Polynomials are really, really common, and I'm really not wanting to do exponentials or trigs unless I absolutely have to. All right. Note, you will be taking the derivative of something, u, whatever you choose to be u, but you'll be taking the integral of the other side. All right. Okay, let's jump in. Okay. I'm looking at example number 1, and it says x e to the x dx. When I look at this, I see two things that are seemingly unrelated. Now, we have done parts where we said, okay, let's let u be x. But it turns out if you take the derivative of u, you get 1. Don't write this down. You're going to get 1 dx. I can't use u sub because I actually have an extra x. So we can't use u sub. We've tried it. We took a look at it, and that's what you should always do is try u sub first. This should not be your immediate go-to. Integration by parts should not be your immediate go-to. So here's what I'm going to do. I'm going to let this, I'm going to pick my u to be something easy. So the first thing I'm going to do is polynomial. So I'm going to let u be the polynomial x. That means that I'm going to let e to the x dx be the dv. Does everybody see what I did? So I have an integral of some u times dv. All right, so I'm pulling out. So everything here, it's almost like if I highlighted, I would have the two parts completely separated. This and this are completely separated. It's almost like I pulled it into two different sections. So I have this and I have this. Now, on the left-hand side, you're going to take the derivative. So right here, we're going to take the derivative. Okay. Over here, you have the derivative of v, and you want to find v. Okay. So what you're going to do here is you're going to take the integral. So you're actually taking the integral of one side, and you're going to take the derivative of the other. Now, for my purposes of what I like to think about, and I hope this helps you, I can imagine putting a little integration symbol right here because this one already has the dx with it. Okay. Now I'm ready to actually do my parts. Let's find what we need. So du is equal to 1 dx. What is my v? If I have dv, my derivative, how do I work backwards? Well, the integral of e to the x dx is e to the x. So now I actually have four parts that I'm actually going to have to do something with. A u, and a dv, a du, and a v. So I have the derivative and I have the original functions. Now, what is my Integration by parts tell me it's going to be my u times my v, u times v, minus the integral of v du. U times v, integral of u times v, minus, oops, nope, it's u times v, minus the integral of v du. Okay, I'm just pulling it down, and I'm going to use this right here. I'll kind of put this right here. All right, so I'm finding the integral of something that seemingly is unrelated that u sub won't work for, and now I'm just going to follow my formula. Equals the u term, which is x, times the v term, which turns out to be e to the x. And I don't have to do anything with it, I just multiply those. Minus the integral of v du, which is the last bottom two parts. V du, which is e to the x, times 1 dx. Now, I can actually work this out. I hope that I can take the integral of the second part. And sure enough, I can take the integral of e to the x, 1 dx. So my final answer equals x e to the x minus the integral of e to the x is e to the x. And because this is an indefinite integral, I must remember plus c. I now have actually solved and found the integral answer for something that seemingly was unrelated that I couldn't previously use u substitution for. Again, integration by parts, it is the last technique that you do need to know. I have a feeling you'll definitely have some problems that you might need to practice this with. Okay. Example number 2 is almost the same problem, except I have x squared. So if I have to pick between x squared and e to the x, I'm going to remember my Lipit, logs, and inverse trig functions, polynomials. So polynomials comes before exponentials, so that means u is going to be x squared. So that means this right here is going to be dv. So I see what I'm doing here? I'm just pulling my things that are seemingly unrelated apart. I cannot use u sub. If I did, I don't have what I need to try u sub. All right. So my dv is e to the x dx. Now I'm going to follow my thing. Okay, I need to take the derivative. So on the left, I'm going to take the derivative. Okay, so du is equal to 2x dx. And remember, that is du dx because it's got an x in it. And I'm multiplying both sides by dx, and that moves it over to the right. Okay, we've done that in the past. So we do have dx. All right, so we're taking the derivative of the left. Over here, we're going to take the integral. So if I take the integral of the left, or excuse me, the right, I already have the dx there, so I could just imagine a big integration symbol there. So v would equal e to the x. All right, so u times v is x squared times e to the x minus the integral of u dx. So e to the x, 2x dx. You can move your constant out front. So if I move the 2 out there, okay, it becomes x squared times e to the x minus 2 the integral of ex x dx. And here's the problem. I cannot do the integral. So in this case, I would have to think about using integration by parts again. Okay, I'd have to think about doing it again. So it is possible to do integration by parts multiple times if necessary. Let me make an observation. Notice that I originally started with x squared. When you integrate it, you always lose a power of x. But I have a smaller power of x here in my integral, but I really need to go ahead and do it one more time, and if I reduce the power of x, I would actually end up with no x in my next attempt at doing integration by parts. However, does anybody recognize this as something we just did back over in example 1? So, in the sake of being a little bit efficient, I'm remembering, you know what, I've already done that once. So instead of me having to do it twice here in the same problem again, I'm just going to go ahead and say, you know what, I have to remember to bring this down. It's x squared e to the x minus, all right, and what was the answer? The answer was x e to the x minus e to the x, and then of course we're going to have plus c on all of these. And that is subtraction, so I have to make sure I do it. Final answer is x squared e to the x minus x e to the x plus e to the x plus c. I don't love it. I can do it, but I don't love it. You have to be at least aware of integration by parts. It is one of the methods. Now, if you are really into this kind of thing, like, oh, I'm challenged by how can I do harder and harder, more complicated integrals? Guess what? Calc 2, here you go. Hit it wide open one of these days. They do a lot of integration techniques going beyond what we're going to be doing here. All right, let's talk about example 3. If you want to pick your u, pick the one that's easy, the one that can be gotten rid of. So my u is going to be x squared, and my dv is going to be sine x dx. All right, I am taking the integral, or the derivative of the left-hand side. So I get 2x dx. And I'm taking the integral of the right. So I'm going to get v is going to be, what's the integral of sine? I believe it's negative cosine x. All right, integration by parts equals u v minus the integral of v du. Let me double check. I don't know if I can, yeah, okay. All right, I've done this quite a bit, but not recently. All right, here we go. Equals u times v x squared times negative cosine of x minus the integral of what? Okay, it's going to be u v du, which is negative cosine x, times 2x dx. And of course, those two negatives are going to make it plus the integral of cosine x, 2x dx. And uh-oh, what's going to happen? Do you see it already? I am going to end up with something else that I have to integrate twice. So we're going to have to do parts again. We cannot integrate this right here a second time. I mean, we actually have two parts, and I don't think I actually want to split that up that way. What do we want to be our u? I'm going to pick the easiest to be my u. My u is going to be 2x. Or if you move your 2 out front, it can just be x. I'm going to pick my u to be x. My order of my lipid, I'm remembering. All right, I pause for just a second. And I realize that I have to do parts twice in this problem. So if I do it twice, I've pulled my 2 out. And I've decided that my u is going to be the simplest thing, x. My dv is actually going to be the cosine x dx, and I've already got my u's and v's. Please remember that if you have a 2 on the outside, that's 2 times everything that this second part's going to give me. So make sure that you think about big brackets. So it's going to be uv, so it's going to be x times sine x minus the integral from what? u dv, or v du, which is sine x 1 dx. Now, did you see it? Did you see what happened when I actually had to do the polynomial factor? Went from x squared, then it went to x to the first, and now when I took the derivative again, I'm reducing the power of that polynomial. So here's going to be my final answer. Negative x squared cosine x plus 2 times x sine x, and I believe I'm going to also distribute the 2 minus 2. The integral of, or the integral of sine x is cosine x, which is negative cosine x. All right, so that's going to make that plus 2 cosine x plus c. All right, just to review, we ended up using the smallest one, the one that can be reduced. The easiest one to take the derivative of is going to be our u. So we used u squared, x squared to be our u. We ended up doing integration by parts. We ended up with an integral right here that we had no way to do an integration for without doing parts again. So we ended up doing parts twice. And when we did parts twice, we ended up with negative x squared cosine x plus 2x times sine x plus 2 cosine x plus c. All right, let's move on to example 4. It says beware of trickery, because now that you're kind of in this mode of, oh, okay, I'm going to have to do this stupid, integration by parts thing. Always check u sub first. So that's kind of why I threw this one in. Always check for u sub first, because if you can, it's the easiest way. So if I do that, I'm going to let the actual exponent be my u, and my derivative of u would be 3x squared dx. I actually have x squared, so in this case I'm going to be able to do u substitution and not have to do integration by parts. So I need a 3 in here, so on the outside I'm going to put 1/3. When I rewrite the integral, I'm going to have 1/3 the integral of e to the u times du. Remember, if you highlighted your parts, e would not be highlighted because x to the third is just, x to the third is just the exponent, and 3x squared dx is in this. The e is not highlighted, so I have to think the integral of e is just an e, so 1/3 e. I need to change it back to my u of x to the third plus c. That one actually did not need integration by parts, but if you're not aware, if you don't remember to look for u sub first, you might fall prey to trying to do this one by integration by parts. All right, what do we think is going to happen with example 5? Do you think we need to try parts, or do we want to try u sub first? I hope that you lean toward the thing, oh, okay, I'm going to try u sub first. If you do u sub first, we're going to let u be the 1 over x. du, which is actually the same thing as x to the negative 1. du would be negative 1 x to the negative 2 power dx, which is the same thing as negative 1 over x squared dx. And if we think about that, that's the integral of 1 over x squared times e to the 1 over x power dx. I actually have 1 over x squared. U sub is going to work, so we're going to use u sub every time we can. All right, if I integrate this, it's going to be the integral of, I do need the negative, so I have to complement from that on the outside, so I do need a negative. I'm going to have e to the u du, which is negative e to the, and I'm going to substitute back in for my u, which is 1 over x plus c. All right, how about number 6? Well, here we go. We can try u sub. Usually we let the of part of our cosine be our u, so let's check it. Okay, if we check it real close, 2x dx. I have an x, but it's x to the third, so I have too many x's. So I can't use u sub. No u sub this time. So I'm going to have to say, okay, let's go back and think about parts, because I'm multiplying two things that are seemingly unrelated. I'm multiplying this, multiplying that, so I'm going to let my u be the easiest, which is x to the third. The polynomial comes before the trig function, so the dv is cosine of x squared dx. All right, here we go. All right, we're going to take the derivative of the u part, 3x squared dx. We're going to take the integral of this part. Okay, so here we go. If we take the integral of that part, we're going to get a v, but I can't do it. Can't do it. What's going to be the problem? We can't take cosine of u. Here's what I need to, what I need to do. If I take, see, I'm going to have to do a little u sub within this parts problem. So if u is x squared, du is going to have to be what? 2x dx. I do not have an x. But wait, I do. What if I took one of these x to the thirds and let it be a part of this one, almost like I'm rewriting it as x squared times cosine x times x dx. If I split my x to the third down into x squared and x, I can make it work. That's going to be what I'm going to have to do. So I'm recognizing that things are not always set up perfectly for myself. So this is going to be x squared, and that's going to make this 2x dx. All right, so here we go. I need 2x dx, so in my little dv part here, I need a times 2. And I did split that, so I do have the extra x here. So I'm going to have a little 1/2 out front. So when I take the derivative, or excuse me, the integral, I'm going to be 1/2. The integral of cosine is sine, and it's sine of x squared. Everybody see what we did there? It's a little bit tough. We had to go back and revisit after we got started. All right, so now we're ready for uv minus the integral of v du. All right, here we go. U times v, x squared times 1/2 sine x squared minus the integral of v du, which is 1/2 sine x squared times 2x dx. I think I can do this because guess what happens? I have to end up doing a little u sub again, and I actually have what I need. So let's just see. U is equal to 2x dx, and I have 2x dx. Getting ahead of myself. All right, so I actually have moved the 1/2 integral out. So this is going to equal x squared. I'm going to bring the 1/2 in front. X times sine x squared minus, I'm going to bring this 1/2 out to the front because I don't need it in there. And the integral of sine x squared is going to be negative cosine of x squared plus c. Cleaning this up a little bit, you actually could factor some stuff out. I'm not going to. Sine x squared plus 1/2 cosine x squared plus c. Okay, we don't love it, but we can do it. All right. All right, we're now to the next page. Just to kind of reiterate some notes here, okay, typically our u is going to be something we want to pick that will go away with successive applications like polynomials, because every time you do the integration by parts, you're taking a derivative and it reduces the derivative power each time. So you can remember Lipit. Logs, logs come first, inverse trig functions, polynomials, exponentials, and trig functions are last. All right, so here we go. Which one do I want to let be my u this time? I believe that's a log right there. So in this case, I'm actually going to take a log, so I'm going to let u be natural log of x. dv is going to have to be the x dx. Does everybody see what I did? So this is going to be my u, and this other part is my dv. All right, so here we go. We're taking the derivative of the left, 1 over x dx, times natural log of the base, which is 1. And if I imagine taking the integral of x dx, I add 1 and divide by 2, so it's going to be x squared over 2. I believe that's it. And here we go. uv, so equals u times v minus the integral of v du. So u times v is natural log of x times x squared over 2, or 1/2 x squared, minus the integral of 1/2 x squared times 1 over x dx. Wonder what happens here. Probably should have left this written. That way it would have been a little easier. X squared over 2. Does anything cancel or simplify in this problem? I believe the x on the bottom can cancel out one of these. And I'm going to end up with the integral, a much simpler looking integral of 1/2 x dx. Okay, here we go. So let's finish this. Natural log of x times x squared over 2 minus the 1/2 is a constant, so I can just bring it out front. And the integral of x squared is going to be x to the second over 2, and plus c. Final answer, natural log of x times x squared over 2 minus 1/4 x squared plus c. Okay, again, natural logs would come before polynomials, although polynomials are usually the ones we do first. Okay, if we actually want to factor anything out to make it look better, what would you factor out? If you wanted to factor, could we factor out a 1/2? This has got a 1/2 in it, and this has got a 1/2 in it, and they both have x squared, so I could factor out 1/2 x squared. So, and I can imagine one up there. So I would have 1/2 and x squared, and what would be left? 1/2 x squared would leave me with natural log of x minus what? 1/2 plus c. Same answer. Just want you to know if sometimes you have to have a multiple choice answer, I always know how to go a little farther and look for it. Okay, hopefully that looks good. Lesson 1. This is going to be the last example in this video because I want you to be able to have something to start with, and tomorrow in class we'll be doing more with integration by parts. Okay, which one do we want to let be du? Okay, Lipit says take the natural logs. Any logs come first, so natural log is going to be my u. And that one's pretty easy because the derivative of natural log is 1 over x dx. So v is going to be, dv is going to end up being x squared and the dx. Okay, so I'm kind of letting this part go together to be my dv. I'm going to imagine taking the integral of this, and the integral of x squared actually turns out to be what? X to the third over 3. So my answer is going to be u times v, natural log times x to the third over 3, minus the integral of v du, which is 1 over x, times x to the third over 3, and then I didn't leave out dx on purpose, it's still there. I think some things simplify here. Can we cancel out 1x on the bottom with one of these up here and have x squared? So I'm going to end up with minus 1/3 the integral of x squared dx. And my final answer is natural log x times x to the third over 3 minus 1/3 times x to the third over 3 plus c. Very similar to the last one. I hope that you see that if you wanted to factor out, what could you factor out? Well, they both have x to the third, and they both have 1/3. So if I factored out 1/3 x to the third, I would be left with natural log of x minus 1/3 plus c. Very similar examples. Hopefully, if you can do the first one, you can do the second one. In these cases, we were always looking for what's the easiest u to take. All right, I'm going to stop right. I'm going to stop right there on the video. Hopefully, you've been able to watch the video and get some good information from it. Integration by parts is not the easiest. I really wish I had done it earlier in the semester, but if I don't do it at all, some of you would be very upset with me when you get ready to take the exam and not have a clue as to even start some of the problems. So, all right, I'll see you tomorrow.